Hello, Chem 1B. This is Chapter 17, Lecture Video 4, and we're going to be talking about two things here. How do we calculate pH when we add a strong acid or a strong base to a buffer system? And we're going to start talking about titrations and how we can calculate pH during a titration. So, how do we calculate the change in pH if we add a strong base to a weak acid? Now, this is kind of like a buffer system, right? It's a two-part problem anytime we add anything strong to something weak, right? The first step here when we add these two together is to deal with the stoichiometry, the neutralization reaction. When we add a strong base to either a buffer system or a weak acid, we have a neutralization step, and that's this reaction here. We have the strong base, the OH minus, reacting with the HX, and this is going to form our X minus and H2O. Now, we really don't care about the water because it's neutral, but we do care about this X minus here. And depending on what is the limiting reactant, we're going to make the assumption in this step that the strong base is the limiting reactant, and we're going to have HX in excess, and we're going to form X minus. Now, if we just do this to a weak acid by itself, we're going to make a buffer system because I will have decreased this guy's concentration a little bit, and we're going to increase this concentration significantly, meaning now that even if I didn't before, I now have a buffer system after I add that strong base, as long as the strong base is the limiting reactant in this reaction. If it's not, then we have a solution of strong base present, and we need to do a calculation that's a neutralization and then calculate the pH based on the remaining strong base in the system. But in this scenario, when OH minus is our limiting reactant, we need to recalculate our our HX concentration after the neutralization and our X minus concentration after the neutralization. And now we have a buffer, so we can use Henderson-Hasselbalch to calculate pH, right? We have Ka, we have the HX concentration, we have the X minus concentration. Plug all that into your Henderson-Hasselbalch equation, and you can get pH. Or if you're not allowed to use the Henderson-Hasselbalch equation because Ka is too large, then plug into an ice table and solve the quadratic. What if I did the opposite? What if I add a strong acid to either a weak base or a buffer? Right? If I add it to a weak base by itself, it's going to react with the weak base. We're going to form HX, and again, we're going to form water, but we really don't care about the water because it's neutral. As long as our strong acid is the limiting reactant, if we just had base in the system, we're going to form a buffer again. If we had a buffer already, then we still have a buffer as long as the strong acid is the limiting reactant. And we need to recalculate our concentrations here of HX and X minus, and then yet again, next step, Henderson-Hasselbalch or an ice table to solve for pH. So let's do a problem. We have a buffer. It's made by adding 0.3 moles of acetic acid to 0.3 moles of sodium acetate to 1 liter of water. The pKa of the buffer is 4.74, and we want to know what's the pH after I add 0.02 moles of NaOH. Well, the first step here is going to be the neutralization step. NaOH is going to react with something in the buffer. Now we have to first figure out what. NaOH is a strong base. Hey, you know what bases react with? They react with acids. So this strong base is going to react with our acetic acid, the HC2H3O2. And we know that that reaction is a double replacement. So we can write it out. I've written out the net ionic here. So it's not, I got rid of the NAs because they're spectator ions. And we're going to form what I like to call an ICF table, which is different from ICE or ice tables in a couple of ways. One, it helps us solve non-equilibrium stoichiometry a little bit. So I like to call it initial, change, and now not equilibrium, but final. Now in ICF tables, we only use moles. Unlike equilibrium, like with ice tables, you can use either molarity or pressure in atmospheres. In ICF tables, there's only one unit allowed, and that's moles. So I'm going to put in my initial moles here. I know that I have 0.3 moles of acetic acid because I was told that in the problem. I also know that I added 0.020 moles of NaOH. Again, told it right here in the problem. We don't really care about water. Again, it's neutral. It's not going to affect pH. And we were also told that we had 0.3 moles of sodium or acetate. Sodium acetate, or just acetate in this case, is what we care about. Now, if we think about what's going to happen here, these two are going to react on a 1-to-1 mole ratio because that's what the balanced equation tells us. Now, you do have to double check this. There is a 1 here. This is balanced already, but if it wasn't, then that would change this problem. So let's look at this part right here. What's my limiting reactant is really the first question. Because it's 1-to-1, I know that the smaller number is going to be my limiting reactant. So I know that at the end of the day, OH minus, there will be none left because it's the limiting reactant. Now that means my change for OH minus was minus 0.020 moles, which means this guy's change is also going to be minus 0.020 moles because they're 1-to-1 as far as the mole ratio goes. I also know that over here we also form 1 mole of acetate for every 1 mole of OH minus we lose. So the change over here is going to be positive 0.020 moles. Now, how do we get the final? Well, we just add the initial and the change like an ice table, but not because we're in moles here. Again, this is in moles. And we get these values. Notice we have significant amounts of weak acid and the weak base. This is a buffer situation. So the next step is now we can use Henderson-Hasselbalch. So again, this is not the equilibrium. This is just strong acid, strong base, or sorry, weak acid, strong base, going to completion, neutralization step. So great. What happens next? Well, we have a buffer. So let's use a Henderson-Hasselbalch equation. Now, we could calculate concentration if you want, but they're actually equal, and it actually doesn't matter here. When the two things are in the same solution, we can always use moles in place of concentration in the Henderson-Hasselbalch equation, because at the end of the day, they're going to be in the same solution if they're a buffer. And therefore, the total volume of the solution is going to be the same number for both the weak acid and its conjugate base. So we're dividing the same number by these numbers by the same value, which means they cancel. We don't have to do it. So you can use moles here in place of concentration if you want. It's what I just did. We know this is our weak acid. It goes down here. We know this is our weak base. It goes up there. We're told in the problem that the pK is 4.74. We plug in, we hit enter on our calculator, we get our pH of the solution. So let's do another example problem here, and this will probably be the last problem for this lecture video. How many moles of HCl must be added to a solution that's 250 milliliters containing 0.5 molar HCHO2 and 0.5 molar sodium formate for a solution to have a pH of 3. This is a different problem than the previous one. This is a little bit harder, actually. So if we want to do this problem, the first step is realizing, hey, we have pH. We know we want it to be 3.00. We know that this is equal to pKa plus the log of whatever our concentration of CHO2 minus is over HCHO2 is. Now, I need to get to this pH by adding an acid, apparently, right? Because I'm adding HCl. This means my initials here are not what I currently have. It's not 0.5. We don't know those values yet, because that's the concentration before I've added HCl. And once I add HCl, these concentrations are going to change, right? Because we're going to have a neutralization step. So let's look at that, right? If I add HCl, what's it going to react with? Well, in this case, it's going to react with the NaCHO2 because that's the weak base present. This is a one-way arrow forming HCHO2 and NaCl technically. Again, if we wrote the net ionic, the NaCl completely cancels out. Now, if we do our ICF table, I don't know how many moles of HCl I'm putting in here. I do have the ability to calculate how many moles of sodium formate and acetic and formic acid I have in the solution because I have the volume of the solution and the molarity. So let's do those calculations really quick. Hopefully you know how to calculate moles from molarity given volume. And if you don't, just ask me in a discussion session or, you know, a email. Okay, and I really don't care about NaCl because it's a neutral salt, which is what we learned how to determine in the last chapter, right? So I know that the pKa of this acid, if I take the negative log of this, is equal to 3.74. And one of the things I can notice here is that 3.0 is within 1 pH range from the pKa, which means we still have a buffer at pH 3. This tells me that HCl is my limiting reactant. So I know that this ice table will be minus X, whatever moles of HCl I need to add to get to pH 3, right? So I'll have 0 left of that. I'll have 0.125 minus X here, and I'll have 0.125 plus X. Now, these two I can plug in to my Henderson-Hasselbalch equation, right? So this gives me 3.0 is equal to 3.74, my pKa, plus the log of my X minus, or my formate, right? This guy, 0.125 minus X. Just erase that really quick. All over 0.125 plus X. Now at this point, we can solve this equation for X. It's just some algebra, right? The first thing I would do, I'm just going to put it over here, is I would subtract over this value, which gives me 0.74 negative is equal to log of all this, right? 0.125 minus X over 0.125 plus X. Now, I can get rid of the log by taking everything to the power 10 to the power of everything, which will get me the next equation. And if I do that, I get 0.182 is equal to 0.125 minus X over 0.125 plus X. At this point, it's a relatively simple algebraic equation to solve for X. And we can get X, and I'm just going to skip the algebra here. If you need me to show it, please just come to discussion session. And you should get about 0.0909 moles of HCl that need to be added. All right, so if you have any questions, please let me know. Discussion session or email are the best ways to reach me.